Hello, welcome back. We are continuing our journey in Chapter 22 of Fundamentals of Inorganic Glasses, which deals with glass forming and glass melting. Last time we had a general introduction to glass technology. Today we are going to dive in deeper into the melting process. So how do we select our batch materials? How do we mix them? What are the reactions that take place during the batch melting process? And then we will get into fining operations, which is how to remove bubbles from your glass melt. So let us dive in. Now, when we consider glass melting, there are various processes that take place. When we say glass melting, there's a whole lot of different components to that. One of them could be drying of raw materials, which is called calcining. If you have any batch materials that are wet, or if they have either fizzy-sorbed or chemi-sorbed water, if there's too much water, that can actually lead to foaming behavior if these hydrated batch materials are put into your glass melting tank. So in that case, it is important to have the batch materials undergo a calcining process first, which means exposing the batch to temperatures of around 200 to 225 degrees Celsius. That is enough to remove a lot of the water from the batch materials, such that the drier batch materials would be put into the melter. Once the batch materials are in the melter, the first materials that melt would be the ones that have a lower melting temperature. And then we also get decomposition of carbonates that releases carbon dioxide gas. There are reactions that occur between components that lead to lower melting temperature eutectics that get formed. Often this is a result of reacting silica with different fluxes, like different modifier oxides. And another thing that can happen too is that since we are at high temperatures and the molten glass is in contact with the ceramic refractory material of the walls of the melter, there can be dissolution of that refractory material, and so it can corrode over time. That can act to contaminate your glass melt at the same time as wear away at the walls of the refractory. So ultimately, though, what we're trying to do is start off with a batch and turn it into a glass. So the batch is a mixture of different crystalline raw materials as well as cullet, or which is recycled glass. And this batch mixture must reach its melting point in order to react to form lower melting temperature reaction products and ultimately end up with a nice homogeneous glass that has the disordered structure of the frozen in molten liquid. That is the goal. How do we get there? First thing we need to do is to select appropriate batch materials. There are several different components to the batch. Most of the batch consists of our network formers. This forms the majority of the glass network. This involves components like quartz sand for silica, can also involve B2O3, Al2O3, P2O5. In order to lower the melting temperature, we may also add fluxes, which are usually modifier compounds like modifier oxides, sodium, potassium, calcium, lead. Fining agents can be used to help remove bubbles, and we'll go into details about fining agents in the latter part of this lecture. We can also add things to change the color of the batch. These are usually transition metal oxides or rare earth oxides. And finally, about 20% of the batch is usually cullet. As I mentioned last time, cullet consists of both recycled glass that comes from outside of the factory. So this is glass that you recycle. It gets crushed up and then sold back to the glass factory as cullet in order to be included into the batch. Cullet can also be generated internally within the factory based on any glass product that fails quality control. That just gets dropped into a bin and then crushed up, and then that internal cullet is also fed back into the melter. Now, when we are selecting raw materials, we need to make sure that we get the right combination of raw materials to give us the desired glass composition. And this composition is commonly given as a percentage in terms of mole percent. composition. And when we're doing the batch, since we're weighing out the batch by weight, we need to convert this mole percent composition of the glass into a weight percent composition. So we can use the weight percent to weigh out how much of each batch material that we need. Now, some rules of thumb are that simple oxides, especially when it comes to some modifiers, simple oxides are often more expensive than salts or other compounds. So, for example, instead of batching sodium as sodium oxide, it is normally batched as sodium carbonate because sodium carbonate is much more abundantly available. Likewise, quicklime or calcium oxide is more often batched as limestone or just lime, which is calcium carbonate, because that is more abundantly available. Even some network formers too, like B2O3, is much less expensive to batch B2O3 as boric acid, which is H3 BO3. If you've got a boric glass that also has sodium, you can batch it as borax because that will give you both sodium oxide as well as B2O3. Now, raw materials are chosen by their chemical composition as well as the type of volatile species that might evolve. So these are gases that get released as the batch material becomes an oxide. It can release gases in the process. Those gases can include carbon dioxide. So carbonate, for example, CaCO3, when that decomposes into calcium oxide, that releases carbon dioxide in the process. If you have a nitrate batch material, that can release nitrogen gas and oxygen gas. And if you've got a hydrated batch material, like boric acid, for example, that would release water vapor. We also need to choose raw materials based on their reactivity with silica and their particle size distribution. We need to make sure that it's not too coarse, because if the particles are too coarse, it won't melt properly. And if the particles are too fine, there's too much surface tension, which can get in the way of the wetting of those batch materials. And we need to make sure that they have suitable purity and suitably low cost. And as I mentioned, about 20% of the total batch by weight is cullet, which is crushed recycled glass, either coming from the recycling stream from outside of the factory or through internal cullet generation within the factory. Now, this table lists some of the common raw materials that are used in glass melting. This is by no means a complete list, but what you can see is that, for example, if you want to batch alumina, one of the ways that to batch alumina is just by straight batching alumina itself, which is Al2O3. Al2O3 is not going to give off any volatiles during glass melting, and so the batch factor here is just 1, meaning that for every gram of Al2O3 that you put into the batch, you get 1 gram of Al2O3 in the glass. You can also get hydrated alumina. This is alumina hydrate, which has 3 molecules of water for every 1 molecule of Al2O3. And in that case, the batch fraction is 0.654, which means that for every 1 gram of this chemical formula that you batch, you're losing 3 water molecules, and therefore you only get 0.654 grams of alumina. And so when one is calculating the amount of each batch material that you need to account for anything that is lost during that process. So any gases that get released. So that would be taking the weight percent of everything that is lost versus the total weight of the material that gets batched. You can also have compounds that will contribute different oxides. For example, feldspar here has potassium oxide, alumina, and 6 silica in that ratio. And so when we consider the batch reactions there for feldspar, every gram of this produces so much of alumina versus potassium oxide versus silica. If we keep going down here, we see boron oxide can be batched as boric acid, which is a hydrated B2O3 with its batch factor. If you want to batch both sodium and boric oxide into your glass, you can batch that as borax, which is this compound here of Na2O and 2B2O3. So this is probably the least expensive way to batch B2O3 into your glass, as long as you also want to include sodium oxide. When it comes to calcium oxide, there is quicklime, which is calcium oxide. That's just a batch factor of 1. You can also have calcium hydrate, which loses a water molecule. But what is most commonly used for batching calcium is calcium carbonate, which loses CO2 and gives you this batch factor of 0.56. You can also get both calcium and magnesium from dolomite. That releases 2 carbon dioxide molecules, and you get 1 each of calcium and magnesium. And what else is here? So we've got nitrates. If you batch a nitrate, KNO3, this needs to convert to K2O, and so this is going to release both nitrogen gas and oxygen gas in the process. So its batch factor is only 0.465. You can also have potassium carbonate to batch potassium, or potash, which is also hydrated here. Silica usually comes from just quartz sand. That's easy because quartz is pure SaO2. If you've got any impurities that have been measured, like small amounts of sodium or iron, then that would really reduce the batch factor to, say, 0.99 something. And sodium here is normally batched as sodium carbonate, which is soda ash. You can also batch it as sodium nitrate. Sodium carbonate would release carbon dioxide as it converts to sodium oxide, and sodium nitrate would release both nitrogen gas and oxygen gas as it becomes sodium oxide. So some of the considerations in batching is that you should generally assume that anything that is hydrated is going to completely lose its water at high temperatures. So anything that is hydrated with physisorbed or chemisorbed water, all that water is going to release at the high temperatures of the melter. The next thing to assume is that anything that's organic is going to burn off completely. And one needs to be very careful with this because as the organics burn off, they are consuming oxygen and they're going to take oxygen from the oxides that are in the glass melt in order to burn out. And what that means is that organics act as reducing agents in your glass melter. And so that one needs to be very careful because you may not want to have your oxides being reduced in your glass melt. So this is especially important if you've got any contamination of your cullet. For example, if any plastics got mistakenly mixed in with your glass, this can be a problem because it's changing the redox state of the glass melter by having these reducing components in there. Anything that's a carbonate, a sulfate, a sulfite, nitrate, nitrite, etc. All of these are going to decompose into oxides, and all of the carbon, sulfur, and nitrogen is going to be gone. All of that is going to be released as the corresponding gases. Also, if you have any halide salts, so fluorides, chlorides, bromides, iodides, all of these are also going to convert to oxides if the melting is done in air, because the glass melt would very much prefer oxygen as its anion instead of the halides. And there's going to be little trace of any fluorine, chlorine, or bromine or iodine left in the glass. One also has to be very careful with those because these produce gases that are quite dangerous and would need to be scrubbed to make sure that nobody breathes them in. Also, any pure element that is added is going to convert to its equivalent oxide form. And the other last thing to consider here, as I've already noted, is that when calculating batch weights, you must first convert the glass composition from mole percent to weight percent. That conversion is easy, of course, based on the weights of the molecular formula here for the glass. So, for example, if you want to obtain 1 kilogram of this potassium, calcium 5 silica glass, what we need to do is count up how many moles that we have of each one of these. 1 mole of potassium oxide, 1 mole of calcium oxide, 5 moles of silica, according to this formula, convert those to equivalent weight percentages using the molecular weights of each of these oxides. This converts to 20.9 weight percent potassium oxide, 12.4 weight percent calcium oxide, and 66.7 weight percent silica. If we want 1 kilogram of batch, we use the weight percents multiplied by the total amount of glass that we want to get. And then this adds up to 1 kilogram worth of glass. The amount of batch that we need to get 1 kilogram of glass is maybe more than 1 kilogram of batch. For example, if you've got potash here, so potassium carbonate or limestone, calcium carbonate, in those cases, carbon dioxide is released, which means that the batch factors here are going to be either less than 1 or greater than 1, depending upon how the conversion is taking place. So we would need to either divide by the batch factors that are less than 1 from the previous table, or conversely just multiply by their reciprocal, which is what is being done here. So if we want to get 209 grams of potassium oxide, we multiply by this batch factor of 1.469, which means that we need 307 grams of potassium carbonate in order to get 209 grams of potassium oxide. Or likewise, for batching calcium oxide with calcium carbonate, we need to take our desired 124 grams of calcium oxide multiplied by its batch factor of 1.786, which means that we need 221.5 grams of calcium carbonate in order to end up with 124 grams of calcium oxide. So the total amount of batch that you get would be adding up all of these weights, and this is something closer to 1.2 kilograms, and then you're losing about 200 grams in carbon dioxide that gets released. And then what you end up with is just 1 kilogram of glass. Now, if we are melting glasses, if we're doing this at a laboratory scale, the way to make small batches of glass is through crucible melting. Crucibles would contain anywhere from tens of grams up through maybe a couple of kilograms or a few kilograms worth of batch material. And some of the considerations for melting in crucibles are, first of all, what material of crucible should you use? Crucibles are available in clay, which is inexpensive and can only be used once, but clay may not be able to withstand the high temperatures and it may react too readily with molten glass. So this is often not the best choice. There's also pulverized slip-cast fused silica, which are also one-time use refractory. This can withstand much higher temperatures and is less reactive compared to clay. Also fairly cheap. And you can also have dense alumina. Alumina crucibles also have low reactivity. They're strong, but they're a bit more expensive compared to silica. All of these ceramic refractories are just single-use crucibles. If you want multi-use crucibles, we need to go to platinum crucibles. Platinum is, of course, very expensive as a precious metal. The nice thing about platinum is that it can withstand very high temperatures, over 1700 degrees C. It is non-reactive with most glass compositions, and you can clean it by using an acid bath, such as hydrofluoric acid. And so you can reuse platinum crucibles. Oftentimes, it's not pure platinum that is used because pure platinum is relatively soft at high temperatures, but you can make an alloy with rhodium, up to, say, 20% rhodium. This makes it much harder. Also decreases the wetting behavior between the molten glass and the crucible material, has better mechanical performance, and can withstand higher temperatures. Platinum can also be alloyed with gold to help reduce some of the wetting behavior. So most of the time it is an alloy of rhodium with platinum to give the best performance. Now, the crucible melting furnaces can either be heated electrically. This is the most common thing, using electrodes in order to have resistance heating to get to the desired temperatures. You can also have gas-fired crucible melting furnaces or induction heating. After the batch is completely melted and homogenized, then you would take the crucible out of the furnace, and you can either cool the glass in the crucible or pour it into molds or just pour it onto a stainless steel tabletop. It can also be poured into a bucket of water to generate cullet, or it can be rolled onto a steel or aluminum plate. So there are many ways of getting the glass out of the crucible based on how quickly you need to cool it to avoid crystallization and what type of shape are you looking for in the final glass. And then the next thing after pouring it out would be to take your glass and put it into an annealing furnace. The annealing furnace should be set at around the annealing point of the glass. Now, that is batch melting. From an industrial point of view, almost all of the glass melting done in industry is in a continuous melter because this is what we can use to make much larger quantities of glasses and never shut it down. So with continuous glass melting, we have the batch that gets fed into just above the melt line of the glass, of the molten glass. The batch gets fed in via a screw feeder, and it gets fed in at a rate that is commensurate with the rate of glass production at the other side. So this batch gets fed in, and what we have here is our molten glass. If this is an electric furnace, then there are electrodes either on the side walls or electrodes sticking up from the bottom of the furnace that are applying a voltage between those electrodes in order to apply heat to the batch into the molten glass. If it is gas fired, then the gas burners actually come above the melt line here. Now, the key thing that we want to do is set up a thermal gradient between the top part of the melt, which is called the crown, and the bottom part of the melt, which is just called the bottom. We need to set up this thermal gradient in order to induce convection. Convection is needed in order to get good homogenization of our glass melt. Now, if it is gas fired, then the hottest part is on the top because the gas burners need to be above the melt line. And that is what is called a hot crown configuration, where the top of the melt here is hotter compared to the bottom. So the thermal gradient for the hot crown configuration would be hotter on top, colder on the bottom. If it is an electrical furnace, it's usually the opposite because we'd be firing through the sides or from the bottom. And in that case, we would have a hot bottom configuration and what's called a cold crown configuration. So it's just reversing the thermal gradient. There are some glass melters too that have both gas and electric. That gives you the maximal amount of control over the thermal gradient because you could independently adjust the temperature at the crown and the temperature at the bottom in that way. So we get convection here in order to get good melting behavior and good homogenization. Now, the glass does not float across the top here to get to the other side of the melter because if that were to happen, there would be a strong chance of having unmelted batch material that just floats across the top. Instead, there is a wall here and a throat at the bottom, and the molten glass needs to exit the melting tank through the bottom here, through this throat. And it could go into a second phase of kind of a second melter here to help improve the homogenization, or it could directly go through this forehearth and into the finer. When it gets to the finer, that's where the highest temperatures are applied. But first, let's take a quick look at some of these glass melting reactions. These are some of the reactions that take place between the batch materials as they are fed into the melter. So quartz sand on its own, it's going to convert into cristobalite at higher temperatures, and it has a melting temperature of 1713 degrees Celsius. With standard soda lime manufacturing, the highest temperature is about 1500 degrees Celsius. So how is it that silica can melt at 1500 degrees C, which is more than 200 degrees lower than its actual melting point? And this is why it's important to consider the details of the batch reactions that take place. So this quartz sand is being loaded into the melter at the same time as limestone, calcium carbonate, and also sodium carbonate. And what happens is that we're going to have decomposition of the sodium carbonate. So the sodium carbonate is going to melt, and then it's going to decompose into sodium oxide plus CO2 gas that gets released. Likewise, the calcium carbonate is going to decompose into calcium oxide plus CO2 gas. So this all happens at 800 and some degrees Celsius, about 825 for the decomposition of calcium carbonate, and about 850 is where the sodium carbonate is going to melt. Now, these modifier oxides are going to react with silica to form lower melting temperature compounds. For example, the sodium oxide that forms will react with silica and make this sodium silicate compound, which is a eutectic at 840 degrees C. And now this it has a much lower melting temperature compared to the pure quartz sand, which means that we're able to melt this at much lower temperatures. So we don't actually need to get up to the melting temperature of silica because of these reactions in forming the compounds with silica. So the reaction process occurs in steps with all of the melting of the lower melting temperature components, the decomposition into oxides, the reaction of the oxides with each other to form lower melting temperature eutectics, and then finally everything becomes melted together. So an example here, this is sodium carbonate. This is melting, forming sodium carbonate liquid and then decomposing to an oxide. The melting occurs at 850 degrees C, followed by this dissociation into oxide plus carbon dioxide. Limestone is going to decompose at 825 degrees C. If you've got boric oxide in the glass and you batch it as boric acid, that boric acid is going to decompose into a boric oxide plus water vapor. And this decomposition reactions commence at 169 degrees Celsius, eventually leading boron oxide, which then in turn melts at 450 degrees C. Now, if we want to get good quality glass products, we have to make sure that we minimize or eliminate any glass melting defects. There are broadly three different types of defects that can occur in glass melting. The first type are solid defects, the second type are gaseous defects, and the third type of defects are inhomogeneities. Solid defects can be classified as either unmelted batch materials. So this is if you fed in a crystalline batch material and it just simply didn't melt. If it didn't melt for whatever reason and you've got this unmelted batch material that appears as an inclusion in your final glass product, this is what is called or known as a stone. The other thing that can happen is that you could have complete melting of your batch materials, but then as you cool the molten glass below its liquidus temperature, now it's thermodynamically favorable for some crystal to appear. And if that crystallization happens, then you could get crystals that appear in your final glass product. This is what's called primary crystallization, if that crystal forms from the composition of the glass itself, simply by cooling it below its liquidus temperature. So that is primary crystallization. We can also have secondary crystallization, which is what occurs when the molten glass reacts with the refractory materials of the melting tank. If it reacts with the melting tank and forms a new crystal as a result of that reaction, either by corroding something from the melting tank, for example, maybe corroding some zirconia from the melting tank, and then forming a zirconia-containing crystal, that is what's called secondary crystallization. So this is crystallization that doesn't just come from the glass itself, but comes from the glass interacting with the refractory material. So these are three different types of solid defects that can occur. If you see a solid defect in your glass that forms, the first thing that you want to do is figure out what type of crystal it is. You could use X-ray diffraction to figure this out. And if it is a batch stone, what this means is that you need to make sure that all of the batch materials spend enough time in the melter and that the melting temperatures are high enough. If it's primary crystallization, that means that you need to make sure that it cools quickly enough to avoid this type of primary crystallization. If it is secondary crystallization, then you probably want to lower the temperatures to reduce the interaction between the molten glass and the refractory material. So you can see it's really important to diagnose where the defect is coming from because the resolution can be the opposite. If it's an unmelted batch material, you'd want to increase the temperature. But if it's secondary crystallization, you'd probably want to decrease the temperature. Anyway, it's important to diagnose the problem so then you can figure out the appropriate path for getting rid of those defects. The next type of defect are gaseous defects. So these are bubbles that you may have in your final glass product. They are called blisters if they're relatively large bubbles, or seeds if they're relatively small bubbles. These can be the result of trapped air. They can be the result of products of decomposition that get trapped. For example, carbon dioxide coming from carbonates that doesn't fully evolve out of the molten glass. It can be nitrogen gas or oxygen gas from nitrates. It can be water from hydrated batch materials. Gases can also result from what's called permeation blistering. So, for example, if you've got water that gets released, and that water could decompose into hydrogen gas and oxygen gas, hydrogen is so small that it could just permeate through the walls of your melting tank, leaving behind the oxygen. So that's another thing to consider. Again, if you see blisters or seeds, what you want to do is figure out what gas is trapped in there. You can use something called blister gas analysis to do that, which is basically running gas chromatography on the gases that are trapped. And then you can tell how much of that gas is, say, carbon dioxide versus nitrogen versus oxygen. If it is air, what that means is that you are maybe have too vigorous mixing in your glass melting tank and need to sort of back off on that. If it is carbon dioxide, that is coming from your carbonate batch materials, and so on. So we'll cover a little bit later how we actually go about finding and getting rid of these gaseous defects by using fining agents. And then the third type of defect that can occur are inhomogeneities, which is called either striae or chord. This is a result of failing to completely homogenize the glass melt. And so you need to make sure that there are enough convection currents set up. So you've got a big enough temperature differential between the crown of the melter and the bottom of the melter. You could also add a stirrer if needed to help deal with chemical inhomogeneities. Well, let's take a closer look at gaseous defects. If you've got a typical soda lime batch, such as this so-called spruce pine batch, which is in form of soda lime that artists use. If you melt 121 grams of that batch of soda lime glass, it will melt down to just 100 grams of glass and then 21 grams of gas that gets released. And if you look at that by volume, that means that the volume of the glass is about 40 cubic centimeters, but the volume of carbon dioxide that gets released is about 10,000 cubic centimeters of carbon dioxide. So it is a large amount of carbon dioxide that gets released from this decomposition process. And that's a lot of bubbles that need to be removed, a lot of volume of this gas that needs to be removed. And the physics that governs this fining process is really governed by Stokes' law. Stokes' law tells us what is the terminal velocity of a rising bubble in some sort of a viscous fluid. So this V here is the terminal velocity of a rising bubble as it rises up through the molten glass. Eta is the viscosity of the melt. Rho is the difference in density between the bubble and the melt. R is the radius of the bubble, and then G is the acceleration due to gravity, 9.81 meters per second squared. So if we want to make the fining process go faster and get rid of the bubbles faster, there are a couple of things that we can do. We can either try to increase the size of the bubble radius because the radius here is coming in as R squared. So if we can increase the size of the bubbles, that would greatly accelerate the velocity of the rise. The other thing we can do is to lower the viscosity because the viscosity is varying by orders of magnitude with temperature. If you heat up the melt, that lowers the viscosity, and a lower viscosity means that it's more fluid, which means that the bubbles can rise up faster. So the main tricks that we want to play are to either lower the viscosity by increasing temperature or increase the size of the bubbles. Either one of those approaches will help to speed up the fining process. So fining occurs more effectively at elevated temperatures or lower viscosities. Now, the other thing we can do to aid in fining is to include a fining agent as part of the batch. Fining agents are chemical agents that are used to help removal of bubbles from the glass melt. And the key to fining agents is that they have multiple oxidation states, where at high temperatures, a reduced state is favored, and that releases oxygen. As the oxygen is released, that increases the size of the bubbles, which enables the bubbles to rise up faster. So there are dissolved gases that migrate to the bubbles already present. This enlarges them. It increases the buoyancy of the bubbles because they're larger and helps accelerate the Stokes fining. So this fact of having larger bubbles that rise faster, this is what's called physical fining, and that is one of the mechanisms by which fining agents work. The second mechanism is chemical fining, and this is as you lower the temperature then of the fining agent as it exits the finer and starts to cool down. At lower temperatures, now the oxidized state of the fining agent is favored, and that means any remaining gaseous oxygen that didn't fine out is going to be reabsorbed into the glass to convert the fining agent from its reduced state back to its oxidized state. So fining agents serve two purposes. One is to help physical fining by releasing oxygen, which enlarges the size of the blisters, enabling them to rise up faster. And then upon cooling, any remaining oxygen gets reabsorbed by converting the fining agent back from its reduced state to its oxidized state. What are some commonly used fining agents? One of them is arsenic oxide. This isn't used as much anymore because of the toxicity as arsenic, but arsenic is a very effective fining agent. So at high temperatures, we've got the As2O5, the oxidized arsenic oxide is going to reduce to As2O3, and that releases an oxygen molecule in the process. At low temperatures, the reverse reaction, the oxidation reaction is favored, and so this reduced form of arsenic oxide reacts with any remaining oxygen gas and then oxidizes back to As2O5. A more commonly used fining agent now is tin oxide. This is also a very effective fining agent and is non-toxic. Tin oxide exists in both an oxidized state, SnO2, so that would be a 4+ cation for tin, and also tin 2+, which is SnO. So at high temperatures, the oxidized SnO2 wants to decompose into tin oxide in its reduced state, releasing oxygen gas, and then the reverse reaction is favored at low temperatures, which reabsorbs the oxygen as the SnO oxidizes to form SnO2. Another commonly used fining agent is cerium oxide. Cerium oxide can convert between the CeO2 state and the Ce2O3 state. Again, the reduced state is favored at high temperatures because high temperatures favors higher entropy, and we obtain higher entropy when there's a gas that gets released. And then the oxidized state is favored at low temperatures because that favors lower entropy, lower energy, so that involves reabsorbing the oxygen gas. I should point out that there are also physical fining agents, like sodium sulfate is often used in soda lime manufacturing. Sodium sulfate does not have a chemical mechanism for fining. It only has a physical mechanism. Sodium sulfate will release sulfate blisters to enlarge the size of the blisters. And so it helps with physical fining, but it doesn't change oxidation state. So it doesn't actually do anything for chemical fining. But it is used because of its low cost in soda lime manufacturing. Now, when we're considering polyvalent cations that can achieve different oxidation states, the redox equilibrium within the glass melt plays a big role in the final structure and properties, especially the coloration of the glass. So, for example, iron oxide can exist as FeO or Fe2O3, and the coloration of a glass containing iron can vary between yellowish and greenish, depending upon the balance between iron 2 oxide and iron 3 oxide. And if you've got more than one polyvalent cation, then they compete with each other for the available oxygen. And we can evaluate that using an Ellingham diagram. So this is not a great image, but the Ellingham diagrams tell you what is the variation of the Gibbs free energy of redox reactions in the glass melt. The lines here show how the Gibbs free energy is changing. And then the slopes of those lines would be the negative of the entropies of those reactions. And so based on these diagrams, you can tell if you've got more than one polyvalent species there, which ones are going to be more thermodynamically likely to consume the oxygen or release oxygen and undergo those types of redox reactions. So the thing to do is to look up the specific thermodynamic reaction, Gibbs free energy of reaction for the relevant redox reactions in your glass melt, and then you can use that to figure out the redox equilibria. All right, that is our overview of glass melting, including fining and defects. Next time, we are going to get into various types of glass forming operations. If you have any questions, please let me know, and I'll see you next time. Thanks, everyone.